Hi, and welcome to this organic synthesis multi-step question walkthrough. It's on an aromatic organic synthesis multi-step, so there might be some thinking to do about directing effects, i.e. which order do the substituents get put onto the ring. So if we start off by having a look at the question, it says aromatic amines such as 4-chlorophenylamine, structure at the bottom down here, can be converted or are intermediates in the manufacture of azo dyes. Now this is an older spec OCR question, so you don't have to worry about azo dyes for the more modern spec. But it says benzene can be converted into 4-chlorophenylamine in the 3 stages shown below. So in the boxes you need to show the structures of the organic products, and you also need to state the chemicals used. There's a little bit of thinking required about what order in which to do it. So we need to plan our answer and consider a few points. So firstly, any functional group substituted onto a benzene ring will be the product of an electrophilic substitution reaction. So in terms of the chemicals used, you'll need to think about the functional groups that are substituted onto the benzene ring and what electrophile will be needed for that to be achieved. And then you think about which order they'd need to be substituted in so as to be located on the 1 and 4 positions. So in other words, the NH2 on position number 1 and the Cl on position 4. So then you can visualize the synthesis by maybe just sketching something along these lines, and you can see that there's 2 intermediates and there's 3 sets of reagents and conditions, just like you can see on the diagram for the question. So we've got several options. You can nitrate the benzene, then reduce the nitrobenzene to phenylamine before chlorinating it. You could nitrate the benzene, then chlorinate, and then reduce. Or you could chlorinate initially, and then nitrate, and then reduce. So this is where the order in which they are substituted comes into play. So let's look at each one in turn. So we've got sequence A. The nitro group is 3,5 directing, and the Cl group has to be in position number 4. But if we reduce the nitro group to the amine group is 2,4 directing like the OH and phenol. In sequence B, the nitro group is 3,5 directing, so the chlorine would not substitute onto position 4 before the nitro group is reduced. And then in sequence number C, chloro group is 2,4 directing, so the nitration then reduction would orientate the groups appropriately according to the desired product. So basically we can throw out sequence B because it doesn't put the chlorine in the right position relative to NH2. So if we get rid of that in our sequence options at the bottom and look at sequence A. So sequence A, although the nitro group is 3,5 directing, the amine group is 2,4 directing. So if we reduce the nitro group to the amine group first, the nitrogen has a lone pair on it, and that delocalizes into the pi system on the aromatic ring, which means you can then chlorinate it at the appropriate place. So that's one possibility. So we could, in that case, put in the nitration chemicals first, concentrated HNO3 and concentrated H2SO4, before reducing it using tin and concentrated HCl, and then finally using chlorine and a halogen carrier such as AlCl3. You could also use FeCl3 or iron and chlorine separately. So if we now look at sequence C, the chloro group is 2,4 directing, so chlorination would direct the nitro group onto position number 4 relative to Cl, so that would work. And then you could go on and reduce the nitro group to NH2. So doing this way, again, you chlorinate using Cl2 and AlCl3. You could also use Fe or Cl2 or FeCl3 as your halogen carrier. Then you nitrate your chlorobenzene, and that puts the nitro group on position number 4 relative to chlorine. And then you simply reduce the nitro group to NH2. Okay, so hopefully this has been a useful look at 2 different approaches to the same question, and also bring in a little bit of directing groups as well. Thanks for listening. Until next time, see you soon.